Hello and welcome back to the course. In today's tutorial, we're going to look at k-means++ and understand how it works and why it's used. So here we've got our data set, and let's say we want to apply k-means. And for argument's sake, let's say that the centroids are initialized in the following way. Then once we apply k-means and all the steps take place, we will end up with these three clusters. So that's quite straightforward. But now let's say we have the same data set and we apply k-means again, but because the centroids are initialized at random, let's say they were initialized in the following way. And then once we apply k-means, we will get a different set of three clusters. And this is not good. The results are different in these two runs of the same machine learning model of this k-means. And they're only different because the initialization of the centroids was different. We didn't change anything else. And this is called the random initialization trap. Why is this a bad thing? Well, two reasons. The main reason is that when you run a machine learning model, like in this case, like clustering, you want it to be deterministic. You want the result to be the same. You don't want to get different results just because of some random initialization at the start of the algorithm. This model is meant to tell you something about your business, something about the problem you have at hand, how your customers or how these data points are clustered. The insight shouldn't depend on some random initialization. It's an insight about the project or the business or this data set. So that's a big concern. And the second thing is that if you look at the data set itself before the clusters are applied, you can kind of intuitively see what the cluster should be. And it looks like the k-means at the top is showing us the correct clusters. The k-means at the bottom, on the other hand, is not showing us the best set of clusters. So that's what we want to avoid, and that's what k-means++ is designed to combat. It's basically the same as k-means, but it adds some steps at the beginning to initialize centroids in a certain way. So let's have a look. We'll first look at the steps and then we'll look at it visually. So step one is the first centroid is chosen at random. Step two is that for every data point, we compute the distance to the nearest of the already selected centroid. Step three is we then use a weighted random selection to pick out the next centroid based on the distance to the existing centroids. And then we repeat steps 2 and 3 until we have all our centroids ready, and then we just apply the standard k-means clustering. Now this might all seem a little bit too much right now, but let's have a look at it visually. So here's our data set. Let's say that the first centroid was initialized here at random. Now what we're going to do, or what k-means++ will do, is it will measure the distance from every remaining data point to this centroid. And then it will take that distance, the value of the distance, and it will square that value. So now we will select the next centroid at random, but it'll be a weighted random selection. So it'll be weighted by this distance squared. So the centroid in the top right, the furthest away, has the highest chance of being picked. And for argument's sake, let's say that it was selected. Now what happens next is we do the procedure again. We measure the distance to the closest centroid. For each data point, we measure distance to the closest centroid. So these would be these ones for the ones on the left, and the ones on the right were closest to the blue centroid. And again, we would square these distances, and the probability of a centroid or a data point being picked as the next centroid will be proportional to that distance squared. So for argument's sake, let's say the bottom one was selected because it has indeed the highest probability. So there we go. That's how centroids would be initialized, and as a result, we would get these three clusters. So one thing to note here is that k-means++ does not guarantee that there will not be an issue in terms of initialization, because it is done at random. But because it's done in a weighted random fashion, the chances of that happening are much lower, and so this does indeed help with the two problems that we saw in the random initialization trap. So there we go. That's what k-means++ is all about, and that's why we use it. I look forward to seeing you back here next time, and until then, enjoy machine learning.